くりレ夢ムです。
ゆっくりマリサだぜ。
Hi, Raimo. Hi, Marissa. Hey guys. The probability of getting exactly 50 heads in 100 coin flips.
ゆっくりしていってね。
Hello, everyone. Welcome back. I want to start with what sounds like the simplest question in probability. You flip a fair coin 100 times. What is the probability that you get exactly 50 heads? Most people answer immediately. 50-50. You flip a coin, heads is 50%, you flip it 100 times, so obviously you should get 50 heads. That's the most likely outcome. It probably happens most of the time. That answer is wrong. Not slightly wrong. Profoundly wrong. The probability of getting exactly 50 heads in 100 flips is roughly 8%. 8%, not 50%, not even close to 50%. The outcome that feels most natural, most expected, most inevitable, happens less than 1 time in 12. And when you understand why, you will never think about probability, randomness, or the word expected the same way again. Let's go. Chapter 1. The trap of the word expected. The confusion begins with language. Specifically, with one word, expected. In everyday speech, expected means likely, common, what you anticipate. If someone says the expected outcome is 50 heads, you hear 50 heads is what usually happens. In mathematics and statistics, expected means something much more specific and much more subtle. The expected value of a random process is the average outcome over a very large number of repetitions. It is a long-run average, not a prediction of what any particular trial will produce. When mathematicians say the expected number of heads in 100 flips is 50, they mean, if you repeated the experiment millions of times and averaged all the results, you would get a number very close to 50. They do not mean that 50 is what usually happens in any single experiment. They do not mean 50 is even particularly likely. This distinction between the expected value and the likely outcome is one of the most important and consistently misunderstood concepts in all of probability theory. It has consequences that reach far beyond coin flips into medicine, finance, insurance, law, and the daily decisions of everyday life. And the coin flip makes it visible in the most direct way possible. Chapter 2. Counting the universe of possibilities. To understand why exactly 50 heads is so rare, we need to think about the total number of ways 100 coin flips can turn out. Each flip has 2 outcomes, heads or tails. 2 flips have 4 possible sequences, heads heads, heads tails, tails heads, tails tails. 3 flips have 8. 4 flips have 16. The number of possible sequences doubles with every additional flip. 100 flips. The total number of possible sequences of heads and tails is 2 multiplied by itself 100 times. The textbook from OpenStax describes it this way. If you could draw 1,000 dots per second, starting from the moment of the Big Bang, you would currently be about 0.00003% of the way to drawing all of them. The number of possible outcomes is so large that it effectively cannot be visualized. Now, within that incomprehensibly vast space of possibilities, how many sequences contain exactly 50 heads? This is a combinatorics problem, a counting problem. The answer is an enormous number, but it is a vanishingly small fraction of the total. When you divide the number of sequences with exactly 50 heads by the total number of sequences, you get approximately 0.0796, about 8%. The most likely individual outcome is not common. It is just less rare than all the others. Chapter 3. The landscape of probability. A bell in the middle of a desert here is where the picture becomes genuinely illuminating. The 8% for exactly 50 heads does not exist in isolation. It sits at the peak of a distribution, a bell-shaped curve that describes the probabilities of all possible outcomes, from 0 heads to 100 heads. 49 heads has almost exactly the same probability as 50 heads. So does 51. 48 and 52 are also very close. The probabilities fall off gradually as you move away from 50 in either direction, and they fall off very steeply once you get more than 15 or 20 away from center. The probability of getting fewer than 35 heads or more than 65 heads is less than 1% combined. Getting fewer than 20 heads or more than 80 heads is so improbable that you could flip coins every second for millions of years and never see it happen. So here's the picture. The probability is spread across a range of outcomes centered on 50. The peak, 50 heads exactly, is only 8%, but the region from 40 to 60 heads captures about 96% of all probability. Getting somewhere between 40 and 60 heads is nearly certain. Getting exactly 50 heads is merely the single most likely specific number. This is the fundamental insight that most people miss. Most likely outcome does not mean probable outcome. It means least unlikely outcome in a competition where no single outcome is very likely at all. Pause. The first question, let me stop here and ask you something directly. Before you watch this video, if someone had asked you to guess the probability of getting exactly 50 heads in 100 flips, what would you have said? And more importantly, does the 8% answer feel wrong to you even now, after the explanation? Does some part of your intuition still want to say it should be higher? If it does, that feeling is important. It is not a sign that you misunderstood the math. It is a sign that your intuition was built for a world of small numbers. 3 flips, 5 flips, 10 flips, and it is being asked to operate in a world of 100. The gap between intuitive probability and mathematical probability widens as the number of trials grows. Understanding that gap is one of the most useful things you can do with a mathematical education. Tell me in the comments what your initial guess was, and whether it has changed. Chapter 4. Jacob Bernoulli and the Birth of Rigorous Probability. The mathematical structure underlying the coin flip problem was formalized in the early 18th century, and the story of how it happened is worth telling. Jacob Bernoulli was born in Basel, Switzerland in 1654, into one of the most mathematically fertile families in European history. The Bernoullis would eventually produce 8 prominent mathematicians across 3 generations, a concentration of mathematical talent with few parallels in the history of science. Jacob was the patriarch of this dynasty, and his greatest contribution was a book he spent 20 years writing and never finished. The book was called Ars Conjectandi, The Art of Conjecturing. Bernoulli died in 1705 with the manuscript incomplete. His nephew Nicholas published it posthumously in 1713. It is widely regarded as the founding document of mathematical probability. The central result of Ars Conjectandi is what we now call the law of large numbers. Bernoulli proved, rigorously for the first time, that as you repeat a random experiment more and more times, the observed frequency of any outcome converges toward the true probability. Flip a fair coin 10 times, and you might get 3 heads or 8 heads. Flip it 10,000 times, and the proportion of heads will be very close to 50%. Flip it 10 million times, and it will be so close to 50% that the difference is negligible. This sounds obvious, but before Bernoulli, it had never been proved. It had been observed empirically, suspected intuitively, but never rigorously established. The question of whether the world is orderly enough that probabilities are stable across repetitions, that the coin does not somehow conspire to fool you, required a proof, and Bernoulli provided it. He was so proud of his result that he reportedly hid it from the mathematical community for 20 years before publishing, unwilling to share it until the proof was fully complete. He wrote in the manuscript, "This, therefore, is the problem that I have proposed to publish in this place, after I have already concealed it for 20 years. Both its novelty and its great utility combined with its equally great difficulty can add to the weight and value of all the other chapters of this theory." From Bernoulli's law of large numbers, the entire modern theory of statistics eventually grew. The concept of the expected value, that average over many repetitions, rests on Bernoulli's foundation. And the coin flip problem, with its surprising 8% answer, is a direct consequence of the mathematical machinery Bernoulli helped build. Chapter 5. Abraham de Moivre and the Shape of Chance. 20 years after Bernoulli's book appeared, a French mathematician living in London made the next great leap. Abraham de Moivre had been born in France in 1667, but spent most of his career in England as a refugee from religious persecution. He was a friend of Isaac Newton and a central figure in the early development of probability theory. He made his living as a private tutor in mathematics, reportedly so poor that he calculated when he would die by tracking the extra minutes he was sleeping each day, predicting the date of his death with eerie accuracy. In 1733, working on the problem of describing the distribution of outcomes in large numbers of coin flips, de Moivre discovered something remarkable. As the number of flips grows large, the distribution of outcomes, the bell-shaped curve of probabilities, takes on a specific, precise mathematical form. The shape converges to what we now call the normal distribution, or the Gaussian curve, the famous bell curve. De Moivre could not have known the full significance of what he found. The normal distribution would later turn out to describe not just coin flips, but measurement errors in astronomy, heights of human beings, lifespans of manufactured components, fluctuations in financial markets, and the distribution of countless natural phenomena. It is, in a deep sense, the shape of accumulated randomness, what you get when you add up many small, independent random effects. The bell curve of the coin flip is not an accident. It is the first appearance of a universal pattern. And the reason the probability of exactly 50 heads is only 8% is baked into the geometry of that curve. At the peak of the bell, the probability density is spread across a wide range, so no single specific value at the center captures a large fraction of the total. Chapter 6. The Gambler's Fallacy. When intuition attacks the surprise at the 8% answer has a psychological cousin that causes real harm in the real world, the gambler's fallacy. The gambler's fallacy is the belief that in a sequence of random independent events, a deviation from the expected proportion in one direction makes a deviation in the opposite direction more likely in the future. If a coin has come up heads 7 times in a row, the gambler's fallacy says tails is due. If a roulette wheel has landed on red 5 times running, black must be coming. If stock prices have fallen for 3 weeks, a rebound is overdue. None of this is true. A fair coin has no memory. The probability of heads on the next flip is exactly 50%, regardless of what happened on the previous 7 flips. The coin does not track its history and try to even things out. Tversky and Kahneman, the psychologists who mapped the landscape of human cognitive error in the 1970s, identified the gambler's fallacy as an instance of what they called the representativeness heuristic. People believe that a small sample should look like the underlying probability distribution, that 4 heads and 4 tails and 8 flips should be more common than 7 heads and 1 tail, not just in the long run, but right now, in this particular sequence. This is the same error that makes people underestimate the 8% answer. They think 50 heads in 100 flips should be common, because 50 out of 100 looks like the underlying probability. They apply the law of large numbers, which is true in the limit, over millions of trials, to a single trial of 100 flips. The law of large numbers is about averages over vast repetitions. It says nothing about what will happen in any particular 100 flips. The gambler's fallacy is not harmless. It influences betting behavior in casinos, investment decisions in financial markets, and even the judgments of juries about whether a coincidence is too improbable to be accidental. Understanding the gap between expected value and likely outcome is not just an academic exercise. It is a practical defense against a category of systematic error that costs people real money and produces real injustice. Pause. The second question here is something I want you to think about. You now know that getting exactly 50 heads in 100 flips happens only 8% of the time. You know that the number you would call most natural or expected is actually quite rare as a specific outcome. And you know that our intuition systematically overpredicts the probability of the expected value. Here's my question: where else in your life are you making this mistake? Where are you expecting the most likely scenario to be probable, when in fact a wide range of other scenarios collectively dominate? Where are you surprised when things don't come out as expected, not because something went wrong, but because the distribution of outcomes is wider than you assumed? Think about project timelines that always run over. Think about conversations that don't go the way you planned them in your head. Think about sports results that defy prediction week after week. The coin flip is a laboratory for a lesson that applies everywhere. The expected value is real and meaningful. It is just not usually what happens. I want to hear your examples in the comments. This one is genuinely worth thinking about. Chapter 7. Standard deviation and the width of randomness, the mathematical tool for describing how spread out outcomes are around the expected value, is called the standard deviation. In the coin flip problem, it tells us precisely how wide the bell curve is, how far from 50 heads we should typically land. For 100 flips of a fair coin, the standard deviation is 5. This means that on roughly 2/3 of all experiments, the number of heads will fall between 45 and 55, within 5 of the expected value in either direction. 5 flips away from 50 out of 100. That is the typical spread of randomness. Not 1 or 2, 5. And on roughly 95% of all experiments, the number of heads will fall between 40 and 60, within 10 of the expected value in either direction. This width, this spread, is why no specific value near the center is very probable. The probability is not concentrated at 50. It is smeared across a range from 40 to 60. 50 gets its modest 8% not because it is particularly favored, but because it is the highest point of a curve that is spread across 20 different values, each of which has a probability of several percent. As the number of flips increases, the standard deviation grows, but it grows much more slowly than the total number of flips. The standard deviation of 10,000 flips is 50, not 500. The proportion of outcomes within a fixed number of standard deviations of the expected value stays constant, but the absolute range of typical outcomes grows. This has a remarkable implication. If you flip a coin 10,000 times, the probability of getting exactly 5,000 heads is much smaller than 8%. It is closer to 1%. The expected value becomes even less likely as a specific outcome as the number of trials grows. But the proportion of heads gets more and more reliably close to 50%. This is the reconciliation of the paradox. More trials means more certainty about proportions and less certainty about exact counts. The law of large numbers tightens the proportion, but the absolute spread of possible outcomes widens. Both are true simultaneously. Epilogue. What the coin teaches today. We started with a coin. We asked a simple question, and the answer, 8%, opened into a landscape of ideas that took 3 centuries of mathematics to fully map. We saw that the expected value of a random process is a long-run average, not a prediction of any individual outcome. We saw that the most likely specific outcome can be simultaneously the single most probable result in a relatively rare event. We met Jacob Bernoulli, who proved that probabilities are stable in the long run and spent 20 years doing it. We met Abraham de Moivre, who discovered that the shape of accumulated randomness is the bell curve. We traced the gambler's fallacy, the systematic human error of applying long-run intuitions to short-run events, and saw its real-world consequences. And we ended with a question that I hope you will carry with you. Where in your own life are you expecting the expected value and being surprised when the actual distribution delivers something different? The coin flip is not a trivial problem. It is a window into the structure of uncertainty, the gap between what we expect and what actually happens, and why that gap is not a failure of the world to cooperate with our intuitions, but a mathematical inevitability written into the nature of randomness itself. A fair coin, flipped fairly, gives you heads 50% of the time in the long run. In any particular 100 flips, it gives you exactly 50 heads about 8% of the time. Both of those facts are true, and holding both of them in your mind at once, without letting one erase the other, that is what it means to think clearly about probability. Thank you so much for watching. If this video added something to the way you think, a like and a subscription genuinely help this work reach more people. Drop your answers in the comments. I read them. And I'll see you next time. The coin is still in the air.